Hello, everyone. Good afternoon, everyone. Good evening, anywhere you are. Thank you for joining us today. Welcome to Maker Public Webinar Series. Today's topic is medium voltage GIS circuit breaker testing. My name is Jumaidi. As ASEAN Application Engineer, I will be acting as moderator for today's presentation and supporting you in technical issue and read your question for the presenter. On the right side your screen, you can see the control panel with the chat box. Please, you can type any question on that chat box during presentation, and I will read it for you on the Q&A session. All information that you need regarding to this webinar, like a copy of presentation, a link of recording, will be sent to you all attendees within 2 work days. Yeah. The presenter today, we are lucky now. We have the Niels Weckland. He's product manager for circuit breaker product from Maker Sweden. Welcome, Niels. And just last information before we start, after you close this webinar, please help us to improve our webinar with join on the survey. Okay, I think without any further delay, we can start. I will hand over to you, Niels. Please, Niels.
Okay. Good afternoon, everybody. Thank you for joining this webinar about medium voltage circuit breaker testing in GIS switchgear, gas insulated switchgear. So as you heard, my name is Niels Weckland, and I'm product manager in the Maker factory in Sweden for the circuit breaker testing equipment. And I've been working with the Maker and Programma for now it's 36 years with breaker testing. So I will just start the presentation now. Yes, the subtitle for this webinar is switching device analysis in gas insulated medium voltage systems. And why I name it switching device analysis is that it's because it's not only covering circuit breaker testing, it's also for other switching devices like disconnector isolator switches and earth switches that you can find in a medium voltage bay. So just go on here. So the contents of this webinar will be first a short recap about switchgear testing in air insulated environment and some challenges in medium voltage GIS testing, and then about a timing method that we name VDS timing, and the prerequisites for that kind of measurement, and something about test hookup and test procedure finally. So then a little bit about medium voltage switchgear in air insulated switchgear. So here you see a typical bay with the two bus bars. You have isolator switches, and you have your power circuit breaker and a grounding switch or earthing switch. There's also another earthing switch here. So yeah, as you see, everything is kind of open and accessible in this kind of substation. So if we go to the traditional method, the testing conditions using a traditional method, what do you have to do to make a test? Firstly, you need to do the clearing of the workspace and apply to the 5 safety rules. Actually, the bay has to be taken out of service completely to be able to test, and you put your devices to the circuit breaker in local mode and so on. And the 5 safety rules, as you know, they are disconnect and isolate the parts to be worked on. And number 2, secure against reconnection. Number 3, verify that the parts are de-energized by measuring stick or something like that. And number 4, carry out earthing and short circuiting according to the international standards. And number 5, arrange protection against adjacent live parts like blocking and so on. So when you test this kind of circuit breaker, you actually test. The tests are made on the primary components, and for some measurements, grounding on one side need to be removed. For instance, if you do timing of the circuit breaker, unless you have a withdrawable breaker, which most of the breakers are nowadays in the medium voltage substation. So the test parameters for a medium voltage circuit breaker in this air insulated switchgear. So provided that you have an accessible test object like a withdrawable breaker, you will be able to do main contact timing, contact resistance, auxiliary contact timing, coil current analysis, and motion measurements, and vacuum check, and so on. All the tests, because your test object is completely available and disconnected from the installation. So now we go on to the gas insulated switchgear. So here you see a typical bay, compact bay. Here it's a single bus bar in this station. So you have the bus bars here. You have and this actually this blue compartment here, that is the compartment that is filled with SF6 gas. So this is a sealed compartment. So you cannot access that. So and here you have your control cubicle on this side. So you see the compartment from the side. So yeah, up here you have your 3-position switch where you can ground, you can disconnect and have it in open position. And the power circuit breaker, it's normally a vacuum breaker in this kind of switch gear. And yeah, the single line diagram, the corresponding single line diagram looks like this. You have your 3-position switch here. It can be grounded in the open position and connected to the bus bar, and your power circuit breaker here. And down here you have your voltage transformer, and this earthing switch is only to ground the voltage transformer actually. So so you cannot ground the circuit breaker with this switch, because this switch goes either to ground or to this part. So the consequence of this is that the only way to to ground this cable, and so is to do it through the circuit breaker, because the only grounding that exists in this configuration is this one up here. This one is, as I said, only used to ground the voltage transformer. So the circuit breaker need to be closed to ground here, and that makes it, of course, difficult to test. It's not only that it's sealed; it's also you're limited in what operations you can do. So the challenges are then due to the encapsulation of the primary components. It's hard to access, or actually it's impossible, almost impossible. In best case, you can access via spare base or cable termination compartments, but that's not feasible in real life. So the method of resolution for this problem then is an alternative way of main contact testing and main contact timing. So this method was developed in cooperation of two companies, net owners, Sina and Westnetz in Germany, and Megger. And the principle is to utilize the capacitive voltage detecting system named VDS, according to this IEC standard that describes this interface, which actually is a capacitive interface, a capacitive voltage divider that actually, here you have your primary circuit, and you have a capacitor here, and you have a over voltage protection, and a coaxial cable that works as a capacitor as well. So actually you have a voltage division between the primary parts here, and this interface then converts the primary voltage into a harmless voltage on the outputs here on your cubicle panel. So these points are actually accessible from inside the substation. It looks like this. There are two different realizations of this interface. You can have a meter built in like this, or sometimes it's only the banana outlets here. So then you have to use a portable meter to see to plug in here to measure. Actually, the reason why this standard was created is just that in this kind of switchgear there is no way to check if the bay is de-energized. So this was a means of this control. So as you can see from the outside that it's really de-energized with this interface. I should also say that even if there is no meter on the outside, you always have these bananas where you can connect your external meter or something. We will go on to your test instrument also. So there are different VDS variants covered by the standard, and they have basically different output impedance. but all of the standards can be converted to the LRM standard via adapter that you can plug in here. Okay, so we go on this VDS interface. How does it look in a single line diagram? So here you have your diagram again, and this symbol means the VDS interface. It's like a capacitor. Sometimes this part here is more like a half circle also. Sorry. Excuse me. So you will see that in other places. So now on to the implementation of the measurements. So first, here we have the VDS interface. You need some very simple signal conditioning, and then you can connect the signal into the timing channel of a test instrument, of a breaker timer. And you can use the standard breaker analyzers, provided that the timing inputs are actually measuring analog signals. Because what you get out from this interface is the AC voltage, of course. So for testing, yeah, the advantage here is that you don't need any clearing. The operations are actually performed in live conditions. However, but you should disconnect the load from your cable to prevent that you have arcings and so on while switching. So that's an important safety measure. And you can also perform other measurements like motion and coil current. We'll come to that later. So how does a VDS recording look like then? So here is a comparison of the VDS measurement. You have it here, close and open. So you see the AC signals. So when the breaker is open, you have a flat signal, and when the breaker closes, you have your AC, and the opposite when you open the breaker. And this is made on the same breaker, but with a conventional measurement here up, the conventional timing, and this verifies that the times are very similar to the conventional, to the offline test, so to say. And there is also in the software, we have a built-in automatic evaluation of the operation times. So in this case, you see the closing times are calculated for each phase, and the same with the opening time. So you see it's a little bit tricky because the AC doesn't disappear immediately. This can actually look a little bit different on different installations. Sometimes it turns quite immediately to 0 volt, but sometimes you have this kind of decay of the signal, so which makes it, of course, more difficult to analyze. But in this case, the software can manage that. So something about prerequisites for this kind of testing. So the substation and respective bay remains live, and that's actually requirement, since the bay is in service, you need to have all the protections still. They must be working to full extent. And the same with interlockings. They shall remain active to full extent. So you don't so to prevent to operating these connectors in wrong way, for example. So and the protection, yeah, since you actually energize the cable side, even though the load is disconnected somewhere else, you still energize the cable, and I mean there is a small risk that something happens with the cable. In that case, your protection should be activated, so that yeah, to prevent a dangerous situation. And you can also, in addition, you can test your grounding and isolating switches. We will come to that later on here in the presentation. So here in this case, in traditional testing, we use the switching commands from the circuit breaker analyzer. So that actually the circuit breaker analyzer sends out the closing and open commands to your coils. So and the channels also measure control voltage and coil current. However, in this kind of test, when it's a live condition, you cannot do that. So the circuit breaker analyzer shall act passively, which means that you have to use the bay controller or remote the control room to initialize all switching commands. So that's important since it's considered as live. And the circuit breaker just records motor and coil currents using current clamps. As you see here, it's connected in the cubicle. And the measurement is started by connecting the closing and opening commands in parallel into the trigger input of the circuit breaker testing device to get your time reference, which is when the coil is energized actually for circuit breaker timing. So the analyzer just actually works as a passively. It just records the current signals, and it starts with an external trigger pulse. For instance, when the closing and opening commands are sent from the control room. So the realization of this test setup is that, yeah, as a help, we have developed a marshalling device. It's called a trig source selector, which organizes your test signals, the trig signals actually. Because when testing a whole bay, you want to test the isolator switch for bus bar 1, the isolator switch for bus bar 2, and the earthing switch, and you do this for close and trip and motor for the circuit breaker, So each of these, the commands for each of these device, the switching device, can be paralleled into this box. So you get only one triggering output that you then connect to your circuit breaker analyzer, to the trigger input, like that. So in that sense, you can do your connections initially, and then you just perform all your tests according to a bay-related organized test sequence. So you don't need to worry about reconnections during your test. Of course, you have to do some connections. You have to move the current clamps and so. So this is an example of a test plan that this customer built up. So it's very organized. You have circuit breaker testing in one folder with your close and open, and then open for system 2, and you have motor current measurement, which you actually see the recording examples of here. Close, open, and here motor current, and you have one folder where below you have the operation of the Q1 on the disconnector switch. So you both record the. Yeah, I should say also, when testing your the other switching devices, you only record the current for the charge for the motor, nothing else, because it's not possible to do more tests on those devices. So yes, you test in both directions, motor current for closed to open and from open to closed, and the same for the earthing switch, and the same for the second disconnector switch, and so on. Yeah, here you see the different symbol for the VDS interface, actually, half circle. Yes, and more about the hookup for circuit breaker test. You have the VDS interface hooked up to the timing module, timing channels, and you have current clamps for the closing current, for the trip coil current, and optionally you can have a motion measurement also, but that requires some precautions we'll talk about later. And these signals, they are measured by the analog channel, and for the 52A and B switches, the auxiliary switches, you can use the auxiliary module to measure timings of auxiliary contacts. When you do the testing of the isolator and earthing switches, you actually you don't use the VDS interface and not the auxiliary contacts either. You only measure the current of the motor for the disconnector to bus bar 1, the earthing switch, and the disconnector for bus bar 2. That's, yeah, simple. So this is just some examples of test sequence principles. So how, but as said here in the text, you have to observe the local conditions and regulations. So coordination with the control room and test permission zone is needed, and important that the test should be with no load. So the remote side needs to be disconnected from all consumers, but still the bay is considered energized and in live conditions with all protections, all interlockings, and so activated. So you can connect then the test equipment for the CB tests, your clamps to the coil currents and motor current, and of course your timings to the VDS interface, and your triggerings to the closing open commands and motor voltage and so on. And then you can start performing your circuit breaker testing. And yeah, the open 1, close, and open 2, system 2. So yeah, I said about motion measurement, it can be a little bit tricky because in live conditions, you don't want to attach something mechanically to the moving parts because you have a spring that is loaded and it's a bit tricky and dangerous if the breaker would operate for some reason. But there are also ways to solve this. You can have a magnetic connection, and which I've seen some customers do. We have also this as a accessory, and another way is to have splines where you can just put in, can connect your transducer to a turning axis or something like that. So one important thing is that this open that you do, the first one, is actually your first trip measurement, because this breaker might have been in service for a long time, not operating at all. So this gives you important information of the condition, that the long time condition of the circuit breaker. You know, as yeah, from previous webinars also, that the coil can get stuck due to dried grease or corrosion or something like that. And after only 1 or 2 operations, that behavior can be masked, or it can be kind of, yeah, you exercise the breaker, so the behavior disappears. So in that reason, it's important to record this first operation, which in this case you get actually for free with this method, without further arrangements or efforts. Okay, and then after doing your breaker test, you can rearrange the current clamps for isolator and earthing switch motor current testing. So that can be, you test the isolating switch for bus bar 1 and for bus bar 2 and so on. And then this part describes how you can attach a transducer. You have all switches in open position, and you turn off the micro circuit breaker for the motor control voltage, and then you can discharge the spring of the circuit breaker. So in this case, all switches are open, which basically should be almost the same as having the breaker or the bay out of service. So in this case, it will be easier to connect a motion transducer if wanted. So, and then of course you can perform further circuit breaker analysis, such as motor current, minimum operating voltage, and motion. Now, yes, inspection, cleaning, and so on. SF6 pressure. So now the last slide. Some conclusions and benefits with the VDS timing in gas insulated switchgear. The challenges are that the medium voltage GIS circuit breakers, their accessibility is difficult, and it's a high demand on uptime. It's hard to get permission to take out a whole station for maintenance, which is needed if you would test the conventional way. And because it's sealed, there is no access to the primary parts, and it could be gas insulated, but also some manufacturers, they have other kinds of insulation like epoxy and so. And the benefits with the VDS timing then is that that you have a safe access to your primary parts through this VDS interface, and the clearing procedure can be omitted. Means that you also save time, and the test object is left in service, offload, and you get also the first behavior documented. So, and overall it's time saving, and it works with the standard circuit breaker analyzers. I should also say that I know that this kind of procedure with testing live and accessing parts of the installation is not allowed in many parts or in many countries. But of course that can change if you can see the benefits of doing this, and actually it's not a big risk either. So that was all from my side of the presentation. I hand over to Zumeidi to see if you have some questions.
Okay, Niels. Let's see the question. Yeah, at this moment, we don't have any question. Maybe we can wait for attendees type the question. Give them 1-2 minutes time for type the question. Okay.
Yeah, sure.
Yeah, please, anyone type the question if you have any question regarding to this topic. Yeah, again, just remind attendees, all attendees again, after you close this webinar, please fill all information regarding to the survey, please join on that survey. Okay, Niels, I think we don't have any question. We can close this webinar. And
okay.
If still have any question after this, please don't hesitate to email directly to the. You can reply from the email when we send you the recording link and also the copy of the presentation. Yeah, you can directly reply that email, or you also can call the mega representative in your country. Okay, again, thank you everyone. Thank you, Niels, for your good presentation and very informative. And hopefully we can meet again in the next webinar. And to attend this, thank you again. Thank you all. Bye-bye.
Thank you,
Goodbye,
Sumedi. Thank you.
everyone.
Thank you, everyone. Goodbye, everyone. Thank you.
Thank you, everybody, for attending. Bye-bye.